Can you? Okay. First, I'd like to thank the organizers for giving me a chance to speak here today. And I'm just going to briefly discuss my research, which over time I realize has been aimed at trying to address resolving things like horizons and singularities in the framework of string theory. Um, so horizons and singularities show up, and they typically represent extreme limits of physical processes. They show up in various ways, such as black holes, cosmology, and we have some nice talks on De Sitter earlier this week. In many cases, they can signal radical changes in geometry or the structure of space-time. They can also lead to strange paradoxes, and they may signal the breakdown of fundamental laws. You may lose predictive power, for example, in singularities. I guess one approach is to accept that they may be a fundamental part of nature, and we deal with the implications that follow. Or another approach is maybe we could consider that such phenomena are consequences of having discarded too many degrees of freedom, which, if you could keep them, could resolve the physics. And so this is, for the moment, I'll choose this latter approach. And the framework that I'm going to use to address this is, of course, as in the title, string theory, which offers us extended degrees of freedom. It's a leading theory of quantum gravity. I don't think I have to convince this crowd too much of this. Where the fundamental objects are strings, branes, extended objects that can vibrate in various ways. It's consistently formulated in 10D, 10 dimensions. It contains the spin 2 graviton as part of the massless spectrum. And worksheet conformal invariance out of the vanishing of the beta functions leads to Einstein's equations. So the two cases I'm going to consider today are black hole horizons and singularities. And for that, I'm going to just briefly touch on something called the fuzzball paradigm, which conjectures that the black hole horizon is replaced by smooth horizonless configurations made from constituents of string theory, which are the microstates of the black hole with the same mass, charge, angular momentum, and scale. And secondly, the second half of the talk, I'm briefly just going to touch on trying to address cosmological singularities in low-dimensional or two-dimensional string theory and the matrix model correspondence, which is a type of duality before the ADS-CFT duality. I won't say anything about the cosmological horizon. I'm not equipped to say anything about that. We have experts here in the room, but it would be interesting to think more about that question as well. So first, why should we be concerned with black hole microstates? Well, a black hole is a region in space-time where light becomes trapped. And this region is defined by the event horizon, and it hides a space-time singularity at r equals 0. At the horizon, time and space sort of switch roles, and the light cone structure tips over and inevitably moves toward the singularity. It was shown that black holes, and this is a well-known thing, that black holes have an entropy which is proportional to the area. And if you put the constants there, this really tells a lot. We have the Boltzmann constant is the speed of light, the gravitational constant, and h bar. So somehow this says that even sort of classically or semi-classically, there's some remnant of quantum gravity that is retained. So maybe one could think of the black hole as a thermodynamic quantity where some sort of microstates have been averaged over. And the question would be, what are these microstates? Furthermore, Hawking showed that black holes do radiate. But in the semi-classical argument, the radiation stems from the vacuum because the vacuum is unstable near the horizon, and the black hole ends up evaporating, but the pairs are entangled. One goes in and one goes out. So you start with something that was a pure state, and it evolves into a mixed state. Or another way to think of it is, I started with the vacuum. So the horizon area is approximately the vacuum for a big black hole, but I end with some radiation. So basically, I start with vacuum, I end with radiation. And how can that happen? You can maybe consider that maybe small corrections could solve this. If somehow the particles were correlated, the outgoing radiation was correlated, but this was shown not to help. And one possible solution is that there are order 1 effects that come into play at the horizon scale. And so for that, so can you support something at the horizon? It's typically really hard in GR to do such a thing. But thankfully, string theory offers some novel objects, extended objects, strings, branes, KK monopoles, various things, which actually can fractionate. So as gravity increases and as the number increases, instead of compressing, branes tend to expand. And so if you could build such things with these fractionated objects, maybe you could support something at the horizon. And furthermore, in string theory, there was sort of a major advance made by Strominger, Vafa, and Sen, of course, which showed that you could count the microstates of a black hole in a field theoretic way, in a regime where the coupling is 0, and it matches the Bekenstein-Hawking entropy. So as I mentioned, one approach is the fuzzball paradigm, which, as I mentioned, it says that the microstates are horizonless, smooth, bound states made from constituents in string theory, and with the same mass charge and angular momentum. And with this framework, one's able to address 2 main aspects, which is the storage of information. And this is typically done if you look at supersymmetric black holes. And then, of course, there's the radiation, the release of information. And you can have notions of solutions from generic to smooth. I guess the generic fuzzball may likely be very, very stringy, maybe non-geometric. But there's a subclass called microstate geometries, which are smooth horizonless solutions in supergravity. And yep. It would be sort of radiate unitarily. Well, you could imagine. So you could imagine I have a configuration and some infalling radiation. What would happen is in this interpretation is that this radiation would sort of bounce around, and maybe at some point it could reemerge as Hawking radiation. Or if I had some sort of non-extremal analog, in this case, you could sort of think of something maybe like excitation sort of joining together and exiting. Oh, that's a good way to think. I never thought about it that way, but interesting. So there's many aspects you can ask about. You know, can you count? Counting is one aspect, and that's, oh. That's right. That's the next slide. Sorry. That's right. That's right. That's on the next slide, actually. Yeah, you're right. So you can ask about dynamics. Can you build the solutions? There's a rich sort of exploration in holography. You can probe the microstructure, and you can ask about observable effects as well. So for the two-charged supersymmetric black holes, these have been constructed either in supergravity or in some sort of string worldsheet model, and they account for the full entropy. But the two-charge case is it's a very small black hole, and what we really want is the three-charge, is to account for the three-charge entropy. And as was mentioned already, so far the smooth states that have been constructed only account for a subleading amount of the entropy, so it's actually down by a total factor of NP to the 1/4. So alpha prime. That's right. The black hole, yes, but I think the solutions, as far as I understand, have been that count that small but finite horizon have been constructed either in supergravity, or I think you can study it from the worldsheet perspective. I think Martinek and company have.
They actually had using special geometry. I think they have the right, R-squared curve and find the correction. So it's just a zero horizon in leading supergravity.
That's right. That's right. It develops a small but finite. That's right. That's right. So.
And it does have the area. Square root of 15 and 5. It actually has that.
So, for the smooth states that have been built so far, typically there's an internal manifold that basically comes along for the ride, but you don't allow anything to depend on the internal manifold. So recent work suggests that you should excite this internal manifold, which for simplicity we take to be T4. But the question is, can you actually build these geometries by including an extra direction? So these they're called superstrata. These three charge. They're functions of 5 variables. So you can build these in 6D supergravity. I don't show any of the solutions, but you can build them in 6D supergravity, and they're functions of 5 variables. And so the question is, can you include another internal direction and build some consistent solutions? And that's work in progress, and it's not clear if it's possible, but we'll see it. That's to be determined. So that's all I'm going to say about this part. And now I just want to move on to some of the work that I've done with Shumit and Sinong, and towards resolving cosmological singularities. And so these types of singularities can appear, for example, a Big Bang or a Big Crunch, or you may have some sort of space-like singularity. And so to address this, we're going to use it's a simpler model in 2D, but it allows you to sort of focus in on addressing the singularity question. So the correspondence between two-dimensional string theory, which has a worldsheet field X and a Louisville field phi, which is due to a C=1 Hermitian matrix model. On the matrix model side, I don't show the steps, but you can rewrite the matrix model as some sort of non-relativistic fermions. And this, in turn, can be written in terms of a collective field theory and fermionic phase space. And so what this does is provides a setting to study time-dependent backgrounds in string theory, which is typically quite difficult, and it's able to yield toy cosmological models, which correspond to dynamics of the Fermi surface. And what you can do is you're able to sort of study the fermionic description and the collective field description and the fermionic description, and you're able to see maybe how the fermionic description can sort of resolve something that looks singular in the collective field description. So typically what one does is one takes some sort of double scaling limit where the coupling of the matrix model is taken to zero, while taken to infinity, while the Fermi energy is taken to zero, and you keep the product constant. And in the matrix model potential, when you do this double scaling limit, you have a term which ends up transforming into an inverted harmonic oscillator potential after you go through the sort of chain of relations. And so you can solve this in terms, you can solve the classical equations of motion in terms of this collective field. And this corresponds to fermions moving in an inverted harmonic oscillator potential. And so then you could ask about fluctuations of this Fermi surface around some sort of leading order saddle solution. And this corresponds to a massless scalar. And actually this massless scalar in the collective field description is related to sort of the massless tachyon in on the worldsheet side. So you can generate time-dependent emergent geometries in various ways. One is you can take time-independent solutions, and you can act with what's called a W infinity algebra on the phase space variables, and they remain solutions, but they become time-dependent. And you can study various regimes. There's a parameter which parameterizes this W infinity transformation. And when you look at different parameters, you can either have smooth evolution, or you may find that there's some sort of space-like singularity where the couplings of the fluctuation diverge. Another way to study the question is you can quench the matrix model, you can quench the coupling, and this corresponds to a quenched inverted harmonic oscillator potential. And then you can study various quench protocols, and you're able to, again, you can derive some sort of emergent space-time. You can study the Penrose diagram, or you can, or various things. And in some cases, there may be some sort of crunch scenario from the collective field perspective, but then the fermionic description shows regular evolution. But then there could be some scenarios where a space evolves and it sort of hits a space-like boundary or a space-like singularity. And in that case, even the classical fermionic description may not be sufficient. And so then one may want to include finite effects. So you identify the singular behavior, and then you can say, let me include another term in the potential. So in the double scaling limit, you have the inverted harmonic oscillator, but there's actually a quartic term, and when they become comparable, is say order of the square root of n, where n is the number of fermions. And so I've been discussing with Shaun since being here, and maybe how to address some of the singularities that occur when you only consider the double scale limit. If you then include the quartic potential, maybe you can resolve that. So there's also finite string coupling effects, which seem to be harder to address. But this is for future work. That's right, that's right. So Uh, hmm. That, yeah, that's right. That's right. Or the square root of n. So I will conclude because maybe we all want to go to dinner. Typically, just to summarize, horizons represent sort of extreme phenomena, and they can lead to strange consequences or radical alterations or various things. Um, and so we can try to address this if we think that it can be resolved. Maybe we can try to address this in the setting of string theory, which in principle is UV complete. And it offers extended objects, strings and branes, which may offer resolving power that sort of traditional matter is not able to. And so we just briefly touched on applying this towards black hole horizons and singularities by looking at black hole microstates. And then we also discussed briefly how to address space-like singularities using a 2D string theory matrix model correspondence. And there's many many follow-ups, many questions. There's a lot of body of work that may seem hidden sort of in this 20-minute presentation, but over the last 20 years in both of these subjects. The matrix model 2D correspondence goes back even further, I guess, than ADS-CFT. But it provides a rich set of structures that we can try to address these questions about horizons and singularities. So with that, I'd like to finish, and thank you all for your attention.
Questions?
This is optimal possible scenario. From the other side, who are sort of opposed to it, what would be the most sort of damaging argument to you? I mean, for those who are not trusting the possible scenario, what would be the most strong argument from them?
You're asking about the space like right?
I mean, black hole.
Black hole.
Yeah, because what? I don't know anything about what. Because I think my understanding, if you talk to the first one, Samir has one notion of what is the first one, Warner and India has another notion of what is called a first one. I think everybody agrees there are microstates of black holes. That I think is fine with everybody. But I think the confusion, in my mind, the confusion comes when you try to associate a smooth geometry with these microstates. And there are some of them on smooth geometry in the ED order. And it's not even clear to my mind, where does this notion of ED order supergravity come? Why is that important, the important criteria? Yeah, I mean, because first one is nothing, right? So, I mean, the entire thing is, it's accessible, right? I mean, it's a cap geometry.
Mm-hmm.
If it is the geometry.
That's right. But a little bit beyond the supergravity is you can formulate this thing. Martinek and Turton and Masai, they have these papers on the world sheet. I think there's some things you can access on the world sheet that even supergravities, yeah, maybe if they intersect or if the branes sort of get close, this W brain picture where light degrees of freedom show up when brains start intersecting. So you do have sort of this Westlemino-Witten technology. Yeah, it's a good question about can you build the leading order solutions in supergravity? There's also alpha prime corrected supergravity, and no one's tried to build solutions in the alpha prime corrected supergravity. I try to look. I mean, for the 3 charge.
Did alpha prime corrected supergravity equal to special geometry, then see what those corrections are. They found a solution, and if the solution is a big horizon, they calculated the area and found that the area is this square root of 225.
That's a 2 charge.
2 charge.
3 charge.
Yeah.
3 charge is the can you produce the leading order in 3 charge?
It could be that that the temperature that different from the extremal platform.
I think people, but there's a Pierre Hodman at Ohio State. He constructed. I don't know how much of the entropy it accounts for, but he constructed a Schwarzschild, smooth Schwarzschild solutions by cycles squeezing in different ways such that it's smooth. So it's still a lot of questions. There's still a lot of questions to be answered, yeah. But it's a top-down approach to try to actually build what the states are. And the cosmological question's even more interesting. It's also very interesting, but yeah, cosmological horizon.
Questions or more comments on Fudgeboard? If not, let's start. Shaun again.